Alright, silly people, here's the situation. We're going to be doing a bunch of stuff with the rotation matrix, that is cosine theta, sine theta, minus sine theta, cosine theta. Um, and that's the two-dimensional rotation matrix specifically. We're not doing 3 dimensions in this one. Uh, First of all, we need to prove that this matrix doesn't have any real eigenvalues. Uh, and so the process for finding eigenvalues is you take the determinant of the matrix determined by your matrix T minus lambda times the identity matrix and set that equal to 0. So we have to take the determinant of the matrix formed by uh, the rotation matrix minus lambda 0, 0, lambda, and set the resultant matrix equal to 0. So it's going to be the determinant of cosine theta minus lambda sine theta minus sine theta cosine theta minus lambda. That determinant is going to be cosine theta minus lambda squared plus sine squared theta. We're going to have to expand the square. So it's cosine squared theta minus 2 lambda cosine theta plus lambda squared plus sine squared theta equals 0. So it's cosine squared plus sine squared makes 1. So that's 1 minus 2 lambda cosine theta plus lambda squared. Or, if you like, c plus b lambda plus a lambda squared. That's right, we're going to use the quadratic formula. So it's negative b plus or minus the square root of b squared minus 4ac all over 2a, right? So b is minus 2 cosine theta, so negative b is actually just 2 cosine theta. Then we get the plus or minus. B squared will be 4 cosine squared theta, and then it's minus 4 times 1 times another 1, so it's just 4 in there, and then this is all divided by 2 down here. So that's cool. We can go ahead and let the cosine theta on the outside of the radical be divided by 2, so now we just have cosine theta plus or minus. We'll factor out 2, because that's the square root of 4 from the radical. And so now it's 2 times the radical cosine squared minus 1 over 2. You can let the 2's cancel each other out. You can again use the sine squared plus cosine squared theta equals 1 identity, but instead rearrange it for cosine squared theta minus 1, and that's going to give you minus sine squared theta. So we actually just have cosine theta plus or minus the square root of minus sine squared theta, which means the square root of that is going to be cosine theta plus or minus I sine theta. This is real. This is only real if sine theta is 0, right? So if you set theta equal to n pi, then your energy or your eigenvalues just turn into cosine of n pi, which is minus 1 to the n. These are the only real eigenvalues, though. So we actually have to solve the problem with arbitrary theta, though, and so all the other ones will be treated pretty much as complex eigenvalues. So we get to keep the I sine theta for each of these. So we'll assign numbers to both of them. We'll call the first eigenvalue cosine theta plus I sine theta, and we'll call the other one lambda 2 cosine theta minus I sine theta. And now we can go about finding the eigenvectors. And those are given by the equation of the rotation matrix times arbitrary eigenvector v1 is equivalent to eigenvalue lambda 1 times vector v1, right? So we can set it up like this. We'll just do the rotation matrix here, cosine theta, and then I'm just going to call the components of the eigenvector v1x and v2, not v2x, let's do v1y for now. And then we know that lambda 1 is cosine theta plus I sine theta. And then the column vector is v1x, v1y. On the left-hand side, we'll do the matrix multiplication and get v1x cosine theta minus v1y sine theta for the first element, and then the second element will be v1x sine theta plus v1y cosine theta. And on the right-hand side, we'll just let the cosine plus I sine move through into the vector. So now we have v1x cosine theta plus v1x I sine theta, and then v1x cosine theta plus v1y, v1y I sine theta. Right. And then this is also supposed to be y here. But yeah, we can go component by component and equate the two sides of the equation now. So just equating the first component on either side, we have this sort of thing going on. Noticeably, the v1x cosine theta cancels out the one that's on the right-hand side, and then you're left with something with a sine function equals something times a sine function. So those cancel out as well, and we're left with minus v1y equals I times v1x. And I'm going to rearrange it so that it's minus sign on this side, actually. But yeah, and then if you, we found one of the components of the eigenvector, so now we can just set the other one. So I'm going to set v1x to 1 so that I can set v1y to minus I, and that will give us the unnormalized v1. Right now it's I minus I. We do have to normalize it, so we take the inner product of v1 with itself and set it equal to 1. So, and there is a normalization constant here, we just haven't figured it out yet. So it's a squared times the row vector 1i times the column vector 1 minus I. Set that equal to 1. So a squared is multiplied by 1 minus I squared. So it's just 1 minus negative 1. So 2. So actually a is equal to 1 over root 2. And we can write finally that v1, the eigenvector, is 1 over root 2 times 1 minus I, right? Same process for the v2. Again, we multiply the arbitrary vector v2 with the rotation matrix on the left-hand side and do the eigenvalue lambda 2 on the right hand side. So we have cosine theta, sine theta, minus sine theta, cosine theta, times v2x, v2y equals, and then the other lambda 2 was cosine theta minus I sine theta, and this is v2x, v2y. Carrying out the matrix multiplication on the left-hand side, this is going to be v2x cosine theta minus v2y sine theta for the first component, and then the second component is v2x sine theta plus v2y cosine theta. And on the right-hand side, both of these are multiplied by the eigenvalue, so it's just v2x cosine theta minus I v2x sine theta, v2y cosine theta minus I v2y sine theta, right? And then again, just sort of setting the first components of the vectors on either side of the equal sign equal to each other, like this, and then noticing that you can cancel out the cosine term again on either side. You can cancel out the minus signs that are going to remain, and you can also cancel out the sine functions that are going to remain. So we have v2y equals I v2x. We can set v2x to 1, so that v2y will be I, and so v2 is as of yet unnormalized eigenvector 1i, and then we can just do the normalization bit. So b squared 1 minus I 1i equals 1, b squared 1 minus I squared equals 1, and then so that's just 2 in there again, so we get that b is 1 over root 2. So we found that the eigenvector v2 is just 1 over root 2 times 1i. Great. Finally, we need to set up the similarity transformation matrices. So now that we have the eigenvectors and eigenvalues, we know that there is a basis that the rotation matrix only has diagonal components, and those diagonal components are the eigenvalues. So there's a version of reality where the rotation matrix just looks like this, right? And actually both of those are instances of Euler's identity, so you can also write it as e to the I theta 0, 0, e to the minus I theta, right? So we just have to find what the new basis, we need to find the similarity transformation to take it into the new basis, and so we're going to end up doing s times t times s inverse to do it, and s inverse is actually going to be formed by the eigenvectors. So for v1, we found that this was 1 over root 2, and this is I over root 2. And then for the second eigenvector, we found this was 1 over root 2, and this was actually the minus I1. v2 was the one with positive I. So this is I over root 2 for that component. So yeah, the columns of the inverse similarity transformation matrix are formed by the eigenvectors, right? Instead of writing it like that, we're going to pull the factor of 1 over root 2 out, and then just have 1 minus I, 1 I here. To get S, it'll actually be the Hermitian conjugate of the inverse because it's a unitary matrix. So we're just going to have to take the transpose and then do the complex conjugate of the transpose. So that looks like 1, 1 here, and then I minus I. Yes, that is what it'll look like. We'll find that the rotation matrix in the new basis where it's diagonalized will be given by st s minus 1. So it's an overall factor of 2 because you're squaring 1 over root 2. S is here, so this is 1, 1, I minus I. Rotation matrix is here, so cosine theta, sine theta, minus sine theta, cosine theta, and then S inverse is here, so 1 minus I, 1 I. We can multiply the last two matrices together, and that gets us cosine theta plus I sine theta, and then cosine theta minus I sine theta here, and then sine theta minus I cosine theta for this one, and then cosine, nope, it's actually sine theta plus I cosine theta, right. Right now, it is actually more useful to try and use Euler's identity on each of these terms. The top left one is just a blatant e to the I theta, and then the top right one is a blatant e to the minus I theta. Let's try to factor out an I from this one. So we'll have a minus I sine theta minus cosine theta in here. And I'm going to move this in a second, but also factoring out an I from the bottom right term, I have an I times minus I sine theta plus cosine theta. This is e to the minus I theta here. So just rewriting those now in terms of e to the I thetas. This is the same. We've got an I times minus e to the I theta. So minus I e to the I theta here. Same guy here. And then this one is going to turn out to be I times e to the minus I theta. Yeah. So that's cool. Now I'm going to multiply the two matrices together. So we have e to the I theta minus I squared e to the I theta, and then e to the I theta plus I squared e to the I theta, e to the minus I theta plus I squared e to the minus I theta, and then finally e to the minus I theta minus I squared e to the minus I theta, right? Of course, I squared is just minus 1, so we actually have 2 e to the I theta here. This will be 0. We've got 0 here, 0 here, and then 2 e to the minus I theta here. You carry out the 1 over 2 out front, and you just get e to the I theta 0, 0, e to the minus I theta. And that is the transformation matrix in the diagonalized basis, so we are good there. All right.